Again, I'm recording this session for those who will not be able to join us today. But today, wait lang, something's wrong. Masyadong malaki yung mukha ko. Itat ko lang. Ayan, okay na yan. Okay, so yung lesson natin again for today is will be focused on the growth part of nucleation and growth. And we also tackle yung elements of grain boundaries. No? Okay. So, we ended with from last yung pinaka last session no, is heterogeneous nucleation, and we noted na si heterogeneous nucleation has the same R star value. Ang difference lang is that instead of they have the same R star value, meaning same lang yung requirements to produce a stable nuclei, pero yung G star or yung energy na kailangan para ma-form yung mga stable nuclei na yun is much smaller than that required of homogeneous nucleation. And that's why in most cases, and dahil din mahirap mag-produce ng pure solutions talaga no, that have no imperfections, usually heterogeneous talaga yung mode of nucleation ng ano natin ng solidification of metals. Okay, and the factor that that affects that G star value is actually yung shape factor, yung S theta na to. Okay? And S theta is given by this shape factor value here. And again, ang assumption nito is parang spherical cap yung object natin. No? Okay? So shape factor is always less than 1. And this value is actually the delta G value no? For homogeneous nucleation. So if you multiply the homogeneous delta G the delta G required for homogeneous nucleation by the shape factor, then you get the delta G star for heterogeneous nucleation. Okay. So let's proceed with growth, no? So in general, meron tayong two types of growth for pure solids. We can either have a continuous growth or pwede tayo magkaroon ng lateral growth. Now, continuous growth occurs in most metals, no, as they have what we call as a rough surface. So kahit if you look at how metals kahit nag-produce tayo ng parang macroscopically smooth metals will always have imperfections, no? And we call this as your rough surfaces, no? And if you could imagine it as a sort of building blocks, although macroscopically parang smooth to, if you look at yung pinaka para on a microscopic scale, meron talaga siyang mga parang ano no, ano tawag dito, mga valleys and mga hills, no, hills and valleys, parang ganito. And we can imagine this as something that looks like this. And when you have a rough surface, ang natural tendency ng material mo or ng specific na species mo, in this particular case yung metal, is to grow continuously, no? Which is different from having a smooth surface. When you have a smooth surface, more lateral yung growth niya. Okay, so to imagine this, just try to imagine this, I don't know, itong scenario na to, itong the one at the top, where you have a liquid that is, or a solid that is solidifying, and you have liquid on top, no? So if you imagine parang, maybe, let me draw, no? Okay. So if you can imagine na meron tayong mga, kunwari lang, I'll just, for simplicity's sake, no? I'll imagine na yung mga stable nuclei natin is parang, or the metal that is parang growing is represented by this block, no? So if you try to have if you have a rough interface, parang mangyari is, if for example ito, this goes down, so parang Tetris block siya, no? So mag-go down siya dyan, you'll notice na wala actually nagbago sa surface niya, no, masyado. Kasi if you look at it, meron tayong in this hollow na instance, ito, kunwari yung ganyan, merong three parts na disconnected, no? Or actually if you look at it from a, ano tawag dito? So for simplicity's sake, let's look at it from a 2D standpoint lang muna, no? So if we look at it, meron tayong three disconnected na ano na atomic crystals. So kumbaga yung, if this is your lattice, may three faces na disconnected. Okay? So if you add this this parang block na to dito, you will also produce 3 pa rin. So meron tayong tatlo pa rin yung disconnections na available sa atin. So kumbaga walang masyadong nagbago sa energy state nung material na to. That's why it will continue growing, no? And you will have multiple ano na to, no? Itong mga hills and valleys na to. And that's why it's easy for a rough interface to proceed or to continuously grow, no? Which is different from when you have a smooth interface, no? Now let's try to imagine a smooth interface. And by the way, for continuous growth, we can approximate the growth velocity by this formula, where the growth velocity is equal to K multiplied by delta T, where delta T is the degree of undercooling, which was discussed earlier, no? And degree of undercooling is just equal to yung melting temperature or freezing, depending on how you look at it, minus the working temperature or yung temperature kung saan natin wino-work on yung material natin. Okay? So almost always, there is always a certain degree of undercooling na kailangan for freezing to occur. Okay? Tapos itong K is is a constant, no, known as your boundary mobility. And you'll notice na as you have a larger degree of undercooling, and sabi natin if larger yung degree of undercooling, if this is the T melting, ang ibig lang sabihin nun is that you are at a temperature that is far away from the going downwards, far away from the melting temperature, no? Okay, so the larger larger the degree of undercooling is, the faster the growth velocity is, which makes sense, no? Because sabi natin na pagka mas mataas yung degree of undercooling natin, the ease of which you solidify your material actually increases, no? Okay. So now let's try to imagine I don't know, yung smooth surface, and this is what happens when you have a smooth surface. Now we call this as lateral growth. So if for example meron tayong and again for simplicity's sake, gawin natin na parang cubes lang yung mga natin mga atoms, tapos meron tayong smooth surface. And usually itong mga a smooth surface occurs when you have yung mga ceramic materials, no? Parang it's more common for ceramic materials than it is for metals. So if you have an arriving atom, for example, ganyan. So at this state, ang only disconnected na surface mo is actually parang, if you think about it, parang kunwari ganyan. So ang disconnected surface mo lang is dito. So kumbaga may isang external surface ka lang. Now when you add this arriving atom right here, you actually add uh, 4 additional phases, no? So 1, 2, 3, no, actually 5 nga dapat. So 4 lang pala, sorry. So this phase, yung nasa kabila, and yung nandito. So hindi ko in-add yung itong kulay puti dito kasi yung original niya, meron naman talagang isang surface pa na nag-i-exist na ngayon. So parang pinalitan mo lang. So ang additional surface lang is actually itong 4 na to. So these additional surfaces are disconnected sila, no? Kumbaga discontinuous yung lattice na yun. So for you to be able to do this, you will require energy, no? So parang mag-increase yung state of energy ng itong solid na to, this growing solid, for you to be able to randomly add this arriving atom. And if you don't have enough surface energy to support this, if you don't have enough driving force to support the additional surface energy, then ang mangyayari is unlikely yung arriving atom mag-grow yung arriving atom through this mechanism, no? So mataas yung probability na itong arriving atom magja-jump back lang din siya papunta sa liquid, no? Because of the lack of free energy. Okay? So a more likely scenario is if you have something like an imperfection like this, no? So kung meron tayong ledge, this is what we call as a ledge. Tapos ito naman, pag ganito yung scenario, we call this as a jug, no? Itong J is what we call as a jug. Tapos itong L is a ledge, no? Okay? So when you have an arriving atom na kunwari ganitong scenario, notice how in this particular scenario, kunwari itong arriving atom pumunta dito sa isang ledge, ang additional na parang discontinuity mo lang is actually 2 lang, no? Itong nandito and doon sa kabilang side. Tama? Kasi ito, this surface right here is already existing. So siya yung pinalitan mo dito na side. Tapos itong surface na to, itong black, existing surface din siya itong nandito. Tama? So, if you look at it, and let me... So, kung titingnan niyo siya, ang ano natin, conclusion natin is that mas konti yung discontinuity na nai-introduce mo, no? So meaning, kung konti yung discontinuity, mas konti din yung additional energy na required para ma-support yung parang additional surfaces na na-produce mo, which in this case is 2, no? As compared to this one, requires 4, right? Now, it's even lower pagka yung arriving atom mo starts at a jug, no? So kunwari itong jug na to, notice how wala kang actually dinagdag na surface area, no? Because this surface area right here, ang original niya is this one. So parang pinalitan mo lang. Itong nasa harap, ang surface area niya is this one. Tapos itong nasa taas naman, ito, ang original surface area niya is nandito sa baba. So meaning, wala kang additional discontinuities or additional surfaces na ini-introduce pagka yung system mo, pagka ganito yung arrangement mo na meron kang jog, no? So it's as if parang nasa rough surface ka lang din na parang additional of of an arriving atom will not introduce any additional discontinuities, and therefore it will just continuously it will have a continuous growth, no? So ito yung likely scenario. It could either be a ledge or a jug, no? And that's why in some cases, ito na yung tinatawag natin na na surface nucleation or lateral growth, na kung saan yung material natin, ang tendency niya is to grow instead of growing upwards, no? Along the rough boundary. Kunwari, kung rough boundary kasi ito, parang may mga hills and valleys ka na ganyan. So pwedeng mag-grow lang siya, arrive lang mga atoms mo dito, tapos continuously mag-grow lang siya pataas, no? So if you have a smooth surface, ang necessary na kailangan mag-produce ka muna ng, if pwedeng ganito, no, through surface nucleation in a manner na meron tayong, kumbaga, if for example merong for some energetic na reason, no, nagkaroon tayo ng parang disc-like na na ledge dito, then pwedeng mag-grow na yung mo, yung solid mo laterally through surface nucleation na parang ganyan. So dito sila mag-grow sa ledge na to. So that could happen, or pwede ring mag-grow sila through a through a defect. So for example, if you look at this defect, this is actually a screw dislocation. So this is a screw dislocation. Hopefully you still remember your types of dislocation, no? So screw dislocations, ito, what happens is yung atoms mo fills out the itong mga jugs na to. So what happens is para siyang mag-grow siya in a spiral, no? Parang ganyan, along the screw dislocation. So if this is your screw dislocation, continuously nag-grow yung solid mo through the arrival of the atoms along the jugs that are being produced, no? And again, for simplicity's sake, para mga blocks lang siya, represented as blocks dito, no? So parang magsa-spiral siya pag ganyan. And that's why a screw dislocation can grow outwards, no? Parang ganyan. So and sometimes tawag nila dito is nucleation through parang a screw dislocation na nucleation. Okay? All right. So that is how you have continuous nucleation and surface nucleation, no? So it can either grow laterally or pwede rin mag-continuous growth siya if it is a rough surface. Okay? Now, dito naman tayo sa heat flow and interface stability. So it matters kung where the solid is growing into, no? So let's first consider a solid. Ito yung solid natin, and this is the interface of that solid. And it's growing with a velocity na b, kunwari, towards the right. Papunta dyan. Tapos, what happens when you are growing into a superheated liquid, meaning that the liquid is hotter than the melting point. So, kumbaga, if you were to visualize kung ito yung TM, a superheated liquid is something that looks like this, no? It is above the melting point. So, when it is above the melting point, when a solid grows in this manner, no? So this is let's just say na hindi naman kasi consistent na no. Kung mag-grow yung solid natin, mag-grow siya with a planar na surface. meron kang mga slight na mga protrusions, no? Or parang perturbations. So, these perturbations ng mga ano natin sa differences in temperature, yung mga ganong factors, can cause a slight protrusion, no? So, if we look at the slight protrusion right here, yung magiging temperature gradient niya will look something like this, no? So since this is hotter than this is a superheated liquid, no? So this liquid here is hotter than the solid, and therefore papasok yung heat flow natin kumbaga is papasok, no? So that is how the temperature gradient looks like. And when you have a heat flow going to this direction, ang mangyayari dyan is dahil yung heat ay papasok dyan, then ang mangyayari is itong protrusion na to will eventually redissolve, no? Because heat is being pumped into this protrusion right here. Tapos ang nangyayari is posible na this is already a solid. Tapos kunwari it is at a temperature lower than T melting. Pero since heat is flowing inside, pwedeng mag-raise yung temperature and eventually mawawala yung protrusion na to, no? So what this means is that for if a solid is growing into a superheated liquid, then impossible na magkaroon ka ng interface stability, no? Ang mangyayari is that eventually itong ano na to, protrusions na to will redissolve, no, and mawawala lang din siya. Okay? So ang result nito is that it can still grow, no? Pero yung mga protrusions natin hindi siya mag-grow outwards, no? So this will move in a what we call as a planar na in a planar manner, no? So kumbaga mawawala lang ng protrusions and solid na planar interface yung mag-grow when you have a superheated na solution, no? Now, let's imagine another scenario wherein meron tayong solid that is growing into a supercooled na solution, no? So, supercooled meaning that the temperature is lower than the melting point. So, if this is the temperature, if this is the melting temperature, then we are working at a temperature that is lower than the melting point. Okay? Now, let's imagine the same scenario. Kung meron tayong mga perturbations ng temperature natin, and this causes a slight protrusion, no? So now that we have this slight protrusion, mangyari is since the solid is hotter, this is hotter than the liquid. So what happens is that heat will be flowing out into the liquid. Tama? So kasi from thermodynamics, we learned that it's always the flow of heat will be always from a region of higher temperature to a region of lower temperature. So a natural tendency is that heat will flow outwards, and when heat flows outwards in this manner, ang mangyayari is in this protrusion right here, ito yung may magkakaroon ng tinatawag na preferential growth, no? So preferential, tama ba yung spelling ko? Preferential growth. Okay. Correct nyo na lang kung mali yung spelling ko. So preferential growth means that this protrusion like right here, because of the thermal gradient, will likely grow out preferentially as compared to itong planar surface na to. And in this particular case, yung advancing na interface will not be anymore a planar interface, no? Mangyayari is it will eventually lead to growth of the protrusion. So parang ganyan. So this growth of the protrusion, if you can imagine it, kunwari meron tayong ganito. Kunwari, if you have a spherical na solid, no? So magkakaroon tayo ng protrusion dito, kunwari. So start natin sa small. Small protrusion siya na ganyan. Because of it's growing into a supercooled liquid, itong protrusion na to will eventually grow out na ganyan. Now we have a planar interface na rin to, no? So posible din na magkaroon siya ng protrusion dito. Tama? Parang ganyan. And yung mga protrusions na yan, pwede rin mag-grow out siya ng ganyan. Producing, and eventually it could produce something that looks like this, no? Na meron tayong mga growth on all sides. So ang tawag natin dito is dendritic na type of growth, no? Dendritic. Comes from the Greek word dendrite ata. Then nakalimutan ko yung Greek word, pero basically it means tree-like yung growth niya, no? Okay, so this is specifically because this is caused by supercooling or the effects of thermal gradients. Ang tawag natin sa mga dendrites na to is a thermal dendrite. No? So this is how those thermal dendrites are formed. Okay, so that's for pure solids. No? Now let's think about alloy solidification naman. So alloy solidification is a little bit complicated, no? Because we have to think about just try to imagine yung phase diagram natin, no? If you look at the phase diagram, kunwari yung pinakasimple natin is, ba't nagkagaganito siya? Okay. Ang gagawin ko? Point corruptions. Oh, so for example, yung simplest natin na phase diagram, it looks something like, ganyan, no? Tapos meron siguro ganyan dito. So that's a simple binary phase diagram, and this is for eutectic na compositions, no? So liquid, this is liquid plus solid 1, liquid plus solid 2, and pasensya na, hindi ko alam kung ano nangyayari, bakit siya biglang nag-spike, no? So this is solid 1 plus solid 2, tapos dito is solid 1, solid 2 naman dito. Okay? So that's a simple na phase diagram, no? And if you look at it, ito actually, ano na to, kung line na to, this one and this one, this is your liquidus line. No? Tama? These are liquidus line. And the liquidus line is actually yung melting point mo. Tama? At any given point, kunwari, any given composition, if you look at the liquidus line, then that is where your T melting is. Kung saan siya nag-touch doon sa liquidus line. Because anything above the liquidus line is a liquid. Anything below, you will now begin to start forming the solid particles. No? So, that is liquidus line. Tapos meron din tayong, ito solidus naman itong nandito, no? Ito sa baba. So, solidus is just anything below, magkakaroon tayo ng anything, or a solidus line is a line that below which only solids exist. So liquidus line above which only liquids exist. Okay. So liquidus is where we have your T melting. So notice how if you have different compositions, no, mag-iiba din yung T melting niya. So for example, this is the lowest point. No? We call this as the eutectic point. And so eutectic point is significantly lower than when it is a solid na object. No? So just to give you parang a basis, a numerical basis. No? Let's look at, for example, yung tin lead. So tin has a pure tin 232 yung ano niya, yung melting point. This is for pure tin. Pure lead has a melting point of 327, pero yung eutectic point nila, which is the lowest point, I forgot, 60-40 yata. I forgot the composition na kung ano yung eutectic composition. Pero yung eutectic na point is only 187. No? So significantly lower yung melting point niya. Okay? So if we have these types of parang differences, no, then it is expected for alloy solidification parang medyo complicated yung magiging ano niya, yung behavior na, because you have different na freezing behaviors over different na compositions. Okay? And it in an ideal world, kunwari ideal yung world, no? If you have a material, itong solid na liquid na to, then everything is homogeneous and we can assume na consistent parati yung melting point at that particular point. So pwede natin assume yun, no? Pero because of the different na mga factors, posible na hindi talaga kumbaga may mga localized areas na magkakaroon ng higher concentrations, may areas na lower concentrations, may enrichment na mangyayari. And because of that, pwedeng move itong melting point, pwede siya mag-move depending on the concentration changes, mag-move left to right. So pwede siya mag-increase, pwede siya mag-decrease, and this will affect your eventual na parang growth behavior, no? Okay? So, ang assumption lang muna natin dito is single phase binary alloys, no? Kasi yun yung pinakamadaling ma-apply, and we can now apply this to more complicated cases. But if you analyze single-phase binary alloys, more specifically yung mga eutectic alloys, no? Then you have the movement of your solid-liquid interface along a bar of alloy. So para ma-simplify natin, let's just assume na meron tayong bar ng alloy and we've restricted it such that we have what we call as directional solidification. No? Tawag natin dito, directional solidification. So ang assumption ng directional solidification is that meron tayong solid liquid interface na ganyan, solid liquid. Tapos mag-grow tayo in this direction. No? And this solid liquid interface is we limit it in such a way na stable siya. It will grow this way. And pwede natin makuha yung parang concentration profile along this bar. No? So we start with x equals 0 and we end with yung x equals yung length ng bar. So pwedeng ganyan. No? So, and we can track kung ano yung behavior natin ng concentration doon sa solid part at pati sa liquid part. And therefore, pwede natin ma-track kung ano yung parang expected na microstructure, expected na na features na makikita natin doon sa solid na growth. No? Okay? So, ito yung, if we analyze this, then we actually have three limiting cases. No? Ito. So the three limiting cases is that, number one, we have equilibrium solidification. So equilibrium solidification just means that everything behaves ideally. No? So the solid will always have homogeneous na composition. Tapos si liquid din will always also have homogeneous na composition. Okay, so that's equilibrium solidification. So parang ideal world to. Tapos then we have solidification with no diffusion in the solid but perfect mixing in the liquid. So in this case, this can be something like meron kang impeller, kunwari doon sa ano mo. Kunwari lang nagsusolidify ka tapos you have perfect mixing in the liquid, and di ko alam kung nangyayari talaga to sa totoong buhay, no? But I think this can occur, no? So parang this is solidification with agitation, kumbaga, parang ganun. But I'm not sure how common it is. So eto, meron kang, kunwari, you have a liquid metal, papasok mo dyan, tapos meron kang impeller such that yung liquid that is, let's just say yung growth ng solidification is something like this. No? So it starts from the bottom plus sides, tapos mag-grow inward siya na ganyan. And therefore, yung mga liquid na nandito will be constantly being mixed together such that homogeneous yung composition ni liquid. So, ang tawag natin sa case na ganyan is solidification with no diffusion in the solid. And this makes sense, no? This is a real world scenario, itong no diffusion in the solid. Because if you imagine it, itong metal natin, this can solidify very quickly, no? And because it solidifies very quickly, then there is not enough time for the solid to diffuse the solute throughout the entirety of the bar. No? So posible na magkaiba yung, kumbaga, iba yung concentration dito sa interface versus sa concentration that has already formed. No? So kumbaga, layer by layer, nag-iiba yung parang concentration niya. Okay? So that is no diffusion in the solid pero perfect mixing sa liquid. And the last scenario is yung quote-unquote worst case scenario, no, wherein wala na ngang diffusion sa solid tapos diffusional mixing lang ang meron sa liquid. So hindi siya perfect mixing. Therefore, kumbaga, the only way that the liquid can distribute its solute is through diffusion mechanism, no, which if it's happening and diffusion is posible kasi na again, yung diffusion does not occur instantaneously, no? So dahil diffusional mixing lang siya, ibig sabihin hindi necessary na yung liquid natin is homogeneous all throughout. Okay? So let's try to track kung ano mangyayari pag meron tayong ganyan. And one important concept when we are talking about this is what we call as the partition coefficient. No? So partition coefficient is just yung XS or the mole fraction of the solute in the solid divided by the mole fraction of the solute in the liquid. And later on, mag-make sense itong value na to. Okay? So, if you have something that looks like this, kunwari ito, this is from a copper aluminum na na case. And let's just say for example na we are solidifying a copper alloy that has a composition of uh, 5% copper. So this has 95% aluminum. No, sorry. 8% copper. Oh, tama. So this is 95% copper. 5% copper, I should say. 5% copper, tapos 95% aluminum. Okay? So kung meron tayong scenario na ganito, we just look at this. Dito muna tayo titingin. No? Look at this and look at this. So notice how sa case na to, magkaiba agad yung yung kumbaga liquidus versus the solidus, no. So this is actually a solidus line ito. Tapos itong this one right here and this one right here kasi this is where you have a kumbaga ang below this lines right here is the where the pure solid exists, and above this line right here is the where the um above which is purely liquid naman siya. Okay? So, meron tayong ganito. So, if you look at it, we can approximate it, no, kasi ito medyo mahirap kasing parang ano, no, naka-curve kasi yan yung actual actual parang phase diagram niya. So we cannot just approximate it to be a linear plot, no. So parang we approximate it na line lang siya, na straight line siya pa ganyan. Just for simplicity's sake, no. And from there, kung meron tayong linear na plots na ganito, pwede na actually natin ma-determine yung K, no, which is in this case 4/44, no, kasi this is the if you take the endpoints, no, ito dito sa dulo, then the concentration of the solid is 4, tapos concentration of the liquid is 44. Okay? So 4/44, that gives us 0.09. Yun yung partition coefficient natin. Okay? So ito, again, idealized to na phase diagram wherein meron tayong straight lang na liquidus and straight lang na solidus lines. Okay? So let's first imagine, no, na meron tayong no diffusion in the solid. Sorry. Imagine muna natin na perfect mixing muna lahat. No? Or homogeneous siya. Hindi pinakita yung... Wait lang. Hindi ko malap. Sige, anyway. Ito pala. Equilibrium solidification. Wait, bakit hindi pinakita? Na-delete ko yata. Wait lang. Hanapin ko lang saglit kasi. Hmm. Wait, drive. My drive. Ito pala. Okay. So, pwede nating i-assume no, kung meron tayong equilibrium solidification that ito, the XS, ito yung concentration niya when it solidifies. Tama kasi for example, if you have something that looks like this, pare nandito ka na sa T2, at the T2, if you use the inverse lever rule, tama pa ba yung pinapakita ko? Wait lang, tama naman. So, this particular case, kung meron kayong at T1, then nagsisimula pa lang mag-form yung ano no, yung first droplets of solids mo. Tapos as you go down the temperature, nag-iiba yung parang concentration ng ano. So if you remember, meron tayong inverse lever rule no. So ito yung amount of solids that has already formed, ito yung remaining liquid. Tapos at the same time, kaya din natin ma-determine yung concentration ng liquid at that particular temperature and concentration of the solid at that particular temperature. Okay? So if you have equilibrium solid, then it makes sense na dapat the solid, ito siya, when it's forming, no? It's, hindi pala ganito yung itsura. Parang it's continuously, ano lang, no? Parang growing. Tapos it's growing in concentration up to the point that it reaches, kasi pagdating mo dito, ito, sa part na to, this is where you have yung maximum concentration mo na, no? So anything above this will result in parang eutectic transformation na. Tama? So you can start growing your solid. So magsisimula siya excess. Tapos after a while, but because you have equilibrium solidification, I'm sorry, it will grow in this manner, no? So for example, um, so at any given point, parang ang nangyayari is because you have a equilibrium solidification such that meron kang diffusion na nangyayari sa solids, tapos yung liquids mo is perfect mixing always, then kahit ano pa mangyari, kunwari itong difference na to, itong area na to is just the difference between the concentration of the X naught or yung original composition of the liquid, and ito naman yung difference ng concentration ng liquid with the original composition. No? So this will change depending on where you are now at the temperature gradient. Pero kumbaga dahil ano siya, fully yung diffusion mo is or meron kang fast enough diffusion dun sa solid, then whatever concentration na meron ka dun sa solid, eventually mag-ano lang din siya, magbabalance out siya. So parang kunwari mag-grow siya ng ganyan. And eventually, pagka nag-reach na to dun sa dulo, itong ano na to, dahil perfect mixing nga siya, mangyayari is it will eventually meet at the X na to. So in a perfect world, ang mangyayari is yung composition mo ng bar will assume the composition of the alloy, no? Which is at X naught. So wala tayong issues dito sa equilibrium solidification. Now, when we have now no diffusion in the solid and we have perfect mixing in the liquid, ganito yung magiging behavior na, no? So, if you look at it, you start off with itong C with a small amount of K. Ito. So, you start with a small amount of solid. Tapos, yung solid mo, as you grow it layer by layer, nangyari is, if you look at it, itong part na to, itong si XS, you'll notice na yung solids mo is getting progressively richer, no? Tama? Parang ganyan. So, nag-i-increase yung composition ng solid mo. So, it means that every layer na pinoproduce mo, so kunwari as it grows layer by layer, nag-i-increase din yung composition ng solid mo. And this is given by Kx not to, because if you remember, X na yung K natin is equal to the composition of the solid divided by the composition of the liquid. Okay? So at the beginning, the composition of the liquid is equal to the composition of the alloy. No? Kasi nag-start ka dito. This is X naught. So your X naught is equal to XL. So therefore, si XS mo at the start, ito, will be equal to KX naught. Okay, so kaya siya KX naught siya. So you start at KX naught, tapos you begin to form slowly by slowly, nag-i-increase siya. No? So from KX naught, nag-i-increase siya slowly paakyat, no? As following this line, itong XS na to. Pero if you if you think about it, yung XS kasi natin is kumbaga we are solidifying progressively, no? So parang as we increase, actually move tong line na to, itong XS na to. It actually follows itong X bar S na line na to, no? So parang ganito, dito siya nagpa-follow. And when it reaches the TE na line, this is the eutectic na temperature line, then mangyayari dyan is magkakaroon tayo ng from liquid, diretso siya magpo-form into the solids. So parang liquid will transform directly into solid 1 and solid 2. Okay? So at any stage during the solidification, meron tayong tinatawag na local equilibrium, no? We can assume this. And this exists between the solid and the liquid interface. That is to say, no, that the composition of the solid and the liquid in contact with one another will be given by the phase diagram. So meron kang kumbaga local equilibrium dito sa at any given point, no? Itong points na to. Okay? So, however, dahil wala tayong yung sinasabi ko kanina, no, wala kasi tayong diffusion in the solid, and therefore yung original compositions niya will perform separate layers. So, which goes to say which is saying na yung mean composition, yung sinasabi ko kanina, itong mean composition X bar S is now different from the composition of the alloy, no? Or the composition of the solid liquid interface. Kasi kanina when we had diffusion, parang ang XS natin is always being raised, no? So for example, kanina nung nag-start tayo with KX naught, kung kani ganyan siya, habang tumataas yung composition natin, tumataas din yung level ng concentration all throughout the bar kasi kumbaga diffusion is occurring. But since dito diffusion is not occurring, ang nangyayari is yung X bar natin, which is the average composition across this bar, is actually lower than the XS, no? So kumbaga hindi yung buong bar, etong XS lang kasi is the composition at the interface, no? Yun yung expected natin. So at the interface, at whatever temperature we are working on, kung kumari nandito na tayo, then at that temperature, we are sure that the interface at the bar separating the liquid and the solid will always be XS. Pero, kumbaga yung overall composition niya is actually lower, no? Nandito lang siya sa etong X bar S na to. Because, again, layer by layer siya nag-move, no? And hindi naman nagkakaroon ng diffusion. So, this means that if that's the case, no, meaning kung wala sa solid yung solute, ibig sabihin nasa liquid yung solute. Tama? That makes sense, no? So, the liquid actually is getting progressively richer. So, kung mas progressively richer siya, mag-iiba na yung, kumbaga, hindi din XL lang yung composition ni liquid. It's actually higher than XL. Okay? And since it's a perfect mixing, parang gaganon lang si liquid, no? Liquid is parang same scenario kanina doon sa perfect mixing ng or diffusion in solids, such that na kumbaga nag-change yung liquid composition homogeneously. Ito, nag-change lang din siya kasi perfect mixing siya. So, ang tendency niya is if we look at it from this standpoint, no, mangyayari is eventually maabot sa point na kumbaga si XL will actually have a eutectic composition, and when it has a eutectic composition, magkakaroon siya ng eutectic transformation. So abot siya sa point na eutectic composition siya, and therefore eutectic transformation, and ito yung magiging itsura ng bar, no? So parang slowly, progressively richer yung KX naught natin until aabot ka sa point wherein you have X max, no? And X max is this point right here. This is your X max. This is the maximum na na solute ng na solute na kayang i-contain ng natin ng single phase na solid. And after that, X max, bigla siya magsa-spike, no? Magsa-spike yung composition ng X up to XE where XE is the eutectic composition. So, pag nag-spike na siya, pag abot niya ng point dito, yung liquid composition natin is at the eutectic composition and therefore eutectic transformation na siya. Mangyayari dito, this part of the from this part of the bar right here, magkakaroon siya ng eutectic na microstructure, no? And if you remember eutectic microstructure, usually represented siya by lamellar na structures, no? Parang ganyan yung mga eutectic. Okay? Kumbaga sabay nag-grow yung two phases of your liquid, no? Right? So, totally different yung magiging itsura dito versus sa itsura dito. Dito, progressively going richer lang siya. Dito, eutectic na yung composition. Okay? Now, in this particular case, pwede actually, we can actually do the math, no? And compute for yung relationship between yung XS with I don't know, with the X naught or yung with the X naught pati yung etong FS na value na to, which is the fractional this the solid fraction, no? So this is XS is the composition of the solid at any given point. Tapos etong FS is the fraction of the solid. So kumbaga kung isipin natin yung inverse lever rule, so kunwari sa inverse lever rule, we have, if this is the liquidus line, no? And this is the solidus line. Tapos, this is our working composition. At any given point, meron tayong, siya nagkaganito, hindi ko rin alam eh. Pero, if meron tayong something like this, the way we compute it is, this is actually Fs, tama? This is Fs, ito is Fl. Okay? So, tapos dito sa endpoint na to, this is XL. Tapos ito is XS. Okay? So, if we have equilibrium conditions, when you are using equilibrium conditions, ang gagamitin lang natin is the lever rule, no? Or the inverse lever rule. So, this is computed by whatever distance this is divided by the total distance, makukuha mo na yung Fs. Tapos, ito namang FL, makukuha mo through, But now, when you have non-equilibrium conditions, also in particular, meron tayong no diffusion in solid and perfect mixing in liquids, hindi mo na magagamit si inverse lever rule, no? Actually, ang gagamitin mo is the Shale equations ang tawag natin dito. Minsan dahil ginagamit siya dahil specifically ginagamit to sa non-equilibrium conditions, ang tawag natin dito is the non-equilibrium lever rule. Okay? So, for equilibrium conditions, inverse lever rule lang ginagamit. Pero for non-equilibrium conditions, we need to use the Shale equations. No? And hindi ko sure kung mapapakita to sa other na subjects. No? Pero there is a program na kaya natin mag-create ng mga phase diagrams of different using thermodynamics. Yung thermocalc. Hindi ko alam kung na-explore nyo na yung thermocalc. Pero if you have explored thermocalc, meron actually doon na na conditions wherein pwede mo i-input kung equilibrium conditions pa siya, equilibrium lever rule yung gagamitin or non-equilibrium lever rule. Tapos i-adjust mo siya tapos mag-iiba yung shape ng phase diagram depending on depending on what you're making, parang cooling curve, equilibrium diagrams or ganyan. So actually pwede mo siyang i-input as a parameter itong si Shale equations. No? So it's interesting. Okay? So that's the Shale equations. And lastly, meron na tayong yung last condition natin, which is no diffusion in the solid. Tapos meron tayong diffusional mixing in the liquid. And in this particular case, yung cooling rate natin will be too fast such that substantial diffusion in the solid is prohibited, same as the conditions before, no? Ito, sa condition number 2. Pero wala tayong stirring or convection in the liquid phase. And the solid that is being rejected into from the solid into the liquid will only be transported away through diffusion, no? And that takes time, no? So posible na you are actually building an enriched na ano, no? So if this is your interface, so yung solid mo dahil nagpo-form tayo ng solid dito, no? Test, nagre-reject siya ng solute papunta dito. So yung rejected na solute na yan will build up dito sa parang ano, no, planar front or sa solidification front. So we call this as a solidification front. Dito sa solidification front natin, there is a build up of enriched liquid, no, which will lead to a different looking microstructure, no. Okay? So in this scenario, ang mangyayari is it's similar to the ano, no, sa kanina. So um we have something that looks like this, na meron tayong increasing pa rin yung sa solid, no? Sa solid side increasing siya, but it increases faster, no? So mas mabilis yung kumbaga yung XS natin is compared to dito medyo slow yung ano niya, no, yung rise ng X naught ng XS mo, or the concentration along the solid bar. Dito naman faster yung rise niya. So it's faster because again, because wala kang perfect mixing sa liquid, yung solute na nire-reject mo doon sa liquid will also increase, kumbaga enrich na yung liquid mo. So dahil enriched na yung liquid mo, ibig sabihin nun, yung eventual solid from that enriched na solidification front uh, will also be kumbaga mas mataas na din yung solid na mag-solidify from that enriched liquid. So kaya siya mas mabilis yung parang growth nito, no, or yung parang increase in the concentration along the bar. Then you will reach a point where you have a steady state growth. Ito siya. So what happens in the steady state growth is that yung concentration profile in the liquid must be such that yung rate at which the solid diffuses down the concentration gradient that is away from the interface is balanced by the rate at which the solid is rejecting the solute, no? Okay? So kumbaga at this steady state, yung enrichment ng ito, 'di ba, nire-reject tayo ng solute. At the same time, dahil meron tayong diffusional mixing, kumbaga aabot siya sa point kung saan, and this could be a short steady state, no? Pwedeng short yung steady state depending on the alloy, pwedeng short, pwedeng long steady state. Pero this just means that at a given point, merong time na yung pag-reject niya ng solute is equal to the rate at which it transports yung rejected solute na yun, ita-transport niya along the different parts o kumbaga magkakaroon tayo ng diffusional mixing, no? So nagba-balance out siya. So dahil nagba-balance out siya, kumbaga ma-achieve natin yung steady state na yun. Okay? So after that, magkakaroon tayo ng yung tinatawag na final transient, and the final transient here is similar to what happens dito, no? Dito sa part na to. So aabot sa point na yung liquid natin will achieve a condition wherein it is fully enriched such that aabot siya sa eutectic composition, and when it has a eutectic composition, magta-transform na siya, magkakaroon na siya it will undergo eutectic transformation, and eutectic transformation is signified by this spike, no? Para magsa-spike ka ng ganyan sa concentration. Tapos itong composition na to is eutectic na yung microstructure na ma-observe natin. Okay? So, ganito yung difference pagka meron tayo no diffusion na solid tapos diffusional mixing lang sa liquid. Okay? So, we can approximate the concentration profile in the liquid using this equation, although hindi na siya masyadong importante sa atin, no? Itong rate na to. Okay? So, I think we can end there, no? And ito, this is more complicated na to. This is the concept of constitutional supercooling na. And maybe I'll just, kasi kulang na tayo sa time, no? I'll have to discuss elements of grain boundaries. So I'll probably send you some readings kung saan nyo makikita itong ano na to, no? Pero Meron pa tayo. Wait lang ha. I'll send you some readings so mga ano na to, no? Itong mga additional na parts na to, and maybe you can read it on your own. No? Um, can I summarize this? Inisip ko kung kaya ko bang masummarize to lahat. Summarize siya. Sige. Kaya lang, we'll have to stop there, no? Tapos proceed na lang tayo dun sa ano. So this is a sort of complicated siya na topic doon on how the microstructures are formed based on the ano no, yung solidification mechanism. So ang essential lang dito is to understand that uh, no one condition is predominant no dito sa conditions na nilagay natin itong nandito. Wait lang, asan yun? So yung limiting cases na nilagay natin dito, we have equilibrium solidification, solidification with no diffusion, perfect mixing, and solidification with no diffusion and only diffusional mixing. Etong conditions na to, walang one predominant sa ano no, sa in actual practice. So it's actually a combination of these three no. So when you are producing your microstructures, you will experience all three of these limiting cases. And it will be a combination of both. So pwedeng mag-experience ka ng ganito lang, homogeneous, so may cases na homogeneous lang talaga siya. May cases na wherein may certain areas na nag-experience ng itong perfect mixing na to. So may ganitong pag-spike. Tapos meron din mga cases wherein meron tayong initial transient, steady state, and final. So it will be a mixture of all of these combined. No? Alright? Okay. So I think gusto ko lang uh, sige, pwede ko sigurong i-cover konti itong mga ano no, itong mga common microstructures that are produced. So we have your cellular and dendritic solidification. So we've already stated kung ano yung how dendritic solidification occurs no. So kung meron tayong protrusion, tapos yung protrusion because of it is flowing into a super cooled liquid, mangyayari is magkakaroon tayo ng parang growth nitong uh, itong growth nitong ang tawag dito, yung protrusion natin, no? And when you have a growth of the protrusion, you will create something parang ganito, no? If you look at this, parang may growth ka na ganyan. Actually, magkakaroon ka ng mga small valleys dito sa part na to. So, parang may certain parts na magre-redissolve into the melt. And because of the redissolution, mangyari is magkakaroon ka ng another perturbations and therefore producing protrusions as well dito sa sides na to. So, eventually producing more ano no, more um protrusions, and those additional protrusions na napoproduce mo, magkakaroon siya ng parang stable na ano no growth, and we call this as cellular growth no. So it's known as a cellular growth because if you look at it from the side, parang ganito siya. So this is a microstructure of that growth no. So if you look at it, para siyang mga protrusions na ganito. Tapos from the top view, mukha siyang mga cells no. So each one of these protrusions is itong cell na to. So instead of thermal yung parang yung kanina yung describe ko is thermal dendrites no. So the cause of the protrusion is through the difference in it is flowing into a ano no, into a super cooled liquid. Ito naman si cellular and dendritic solidification, ang cause naman niya is what we call as constitutional supercooling no. So, in a nutshell, no, yung supercooling na to is not because of, kumbaga, if you have, this is a gradient to, itong mga lines na to, this is a gradient, and there is a critical gradient wherein ma-avoid mo itong TE na line, no. So, TE here is the equilibrium na temperature wherein kumbaga, ito yung liquidus temperature natin. So, this is the liquidus temperature. So, kumbaga yung equilibrium melting point, kumbaga. Ito yung magiging profile niya along as you go from the solid bar ko. Ito kasi yung distance, no, as you go along. So ito yung magiging profile niya na ganyan. So there exists a certain critical gradient, no? And this critical gradient is given by this value right here, itong d over v, where d is diffusivity, v is the velocity of the solidification front. So if you reach the critical gradient, then you won't have any constitutional supercooling, no? Anything slower than the critical gradient. So if your critical gradient is, so let's say for example, you follow this TL right here. So this is a slower na gradient, no? So again, ito is parang, kumbaga, itong gradients na to is parang change in temperature over distance. Okay? So if you have uh, a slower gradient right here, yung, kumbaga, if you look at a certain point, kunwari dito ka nakatingin, oops. If you look at something like this, kunwari, no, you'll notice that at this particular point, ang temperature mo is lower than the equilibrium temperature. And therefore, nagkaroon ka ng supercooling because supercooling is technically Tm minus T, di ba? Supercooling, and I'm not sure if na-mention ko na to, supercooling is just the same as undercooling. So they are synonymous terms. Some textbooks mas gusto nilang gamitin yung supercooling, pero the textbooks I use, they prefer the term undercooling, no? Okay? So but basically it means the same thing. So if you look at this, kumbaga ang supercooling na to is not caused by kumbaga hindi siya caused by an increase or decrease in temperature. So ang supercooling na to is caused because of the composition. Okay? So hence the term constitutional supercooling, no? Um, in a way, parang we are saying na yung supercooling arises from the compositional effects ng ng material natin as it solidifies, no? So because of the compositional effects, and hindi siya dahil sa thermal lang, na kumbaga purely through thermal na measurements, then ang kaya natin tinatawag na constitutional supercooling siya. Okay? So if you have constitutional supercooling, then ang likely na magiging behavior is itong cellular or dendritic solidification. So it's much the same way siya as yung kanina, yung may thermal tayo, growing into a super cooled na liquid, pero this time we are growing into super cooled liquid caused by your differences in composition. Okay? Or in a way, parang sinasabi natin na in this particular case, we are growing into a constitutionally supercooled liquid. Okay? If that makes more sense, no? Right? So, ang makikita natin is something that looks like this. Tapos, ito naman, eutectic solidification. I've touched on this before, na pagka magkaroon tayo ng eutectic na transformation, that is saying na yung liquid natin reaches a point where it is enriched enough to reach the eutectic composition. And when you have eutectic composition, yung liquid na yon transforms directly into your alpha plus beta, which is your two solid phases, no? Okay? So pwede ring S1 and S2 to. Okay? So ang normal na ano tawag dito, yung formation niya is to produce a lamellar structure, no? And lamellar structures are yung mga kakaroon ka ng alternate lamellae, no? And these are rods that are embedded in other phases, no? So you have something, and this is an example of a I don't know, eutectic solidification, actual microstructure. Tapos steel, actually kung titingnan mo yung steel, yung perlite is actually eutectoid pala yun. Sorry. Ito eutectic composition. Eutectic compositions usually mapoproduce ka ng lamellar structure that looks like this, no? Okay? Ganito yung behavior ng lamellar structure, no? So parang ang nangyayari is yung si alpha mo, which is the A-rich na phase, tapos si beta, which is the B-rich phase. They're constantly rejecting solute, no? Kasi di ba pag nagso-solidify tayo, nagre-reject tayo ng solute. Tapos yung solute na re-reject is actually napupunta dun sa kabilang sa kabilang solidification front. Parang ganito. So meron kang, if you isolate two solidification fronts, kunwari ganito, and ito. So yung beta mo is a B-rich phase, therefore nagre-reject siya ng A na solute, and the A solute will be kumbaga absorbed in a way by the uh, A-rich phase, which is the alpha phase. Tapos similarly, si alpha-rich phase nagre-reject ng B solute, as ng B solute na to will be rejected into the will be absorbed kumbaga into the beta phase. So parang ang mangyayari is sabay silang mag-grow. Ito, producing a lamellar structure. No? So parang ganyan. And if we have multiple such rods, no, parang ganyan, rod-like structures, then we produce the lamellar structures. Parang makikita natin yung mga ganito. No? Okay. Ito naman, solidification of ingots and castings. This is when we have, usually ganito yung makikita natin for cast structures, no? Yung first na outer layer ito, this is the layer that is in contact with your mold walls, and therefore sila yung pinakamataas yung thermal gradient, no? Or yung parang yung absorb ng heat. So yung from redirection of heat from the liquid to the mold walls is very fast or is very high in this particular region, and therefore sobrang daming kang napoproduce na nucleation sites, no? So in general, if your nucleation is faster than if nucleation is faster than growth, then you will produce smaller grain sizes. But if your growth is faster than nucleation, then you will produce larger na grain sizes. No? So this is what happens dito sa case na to. So ang nangyari is nucleation is very much faster than the growth, and therefore ang nangyari is you have a myriad of grains that are being produced, and this produces a very fine-grained structure along the mold wall. No? So along the mold walls, ang tawag natin sa fine-grained structure na yun is the chill zone. Tapos after the chill zone, because meron ka ng solid na na-produce, no? So the gradient will not be as drastic, no, or mas as steep. So mangyayari is magso-slow down yung heat transfer. So dahil meron na ka ng parang in a way parang insulator siya if you think about it. So yung heat flow from this area right here to this mold wall, kasi yun yung cold interface natin, no? So nagsa-start yung solidification natin from the mold wall papasok. Solidification starts from mold wall papasok dito sa gitna. Okay? So dahil nag-slow down na yung natin gradient natin, nagpo-produce tayo ng larger grains, no? And what happens here is magkakaroon din tayo ng preferential growth, no? And it is kumbaga in the if you imagine it, no? So the growth of the the growth of the solid could be anywhere, no? Pwede siyang mag-grow sideways na ganyan. Grow sideways na also can grow itong parang at an angle dito. Pero since this is for simplicity's sake, let's just imagine na this is a flat surface, no, na parang perfectly straight siya. You will notice na yung gradient will actually be the highest at the at an angle that is perpendicular, no? Which makes sense, tama? Kasi kung perpendicular siya, yun yung kumbaga pinaka-direct, kumbaga walang sign siya. If I can make an analogy, no? Wala siyang sign value, and therefore parang straight lang siya, therefore yun yung highest na yung thermal gradient natin. And therefore, kung highest yung thermal gradient doon sa area na yon, then mas likely na magkakaroon tayo ng solidification. And that's why magkakaroon tayo ng preferential growth, no? So ito, there can be growth in several directions, pero dahil merong certain parang directions that are thermally favorable, mangyayari is hindi na mag-grow out itong mga crystals that are not growing according to the preferential na direction, which is in this case a perpendicular direction. And that's why ang mangyayari is magkakaroon tayo ng parang columnar grains, no? So it will produce very large grains. Ito, kumbaga mag-grow out siya, producing large grains, and these are they grow in columns, no? And that's hence the name columnar zone. Tapos after the columnar zone, abot tayo sa point wherein yung columnar zone natin, eventually abot tayo sa point na ang remaining liquid, kumbaga masyado tayong malayo na sa no, mold wall such that hindi na nagmamatter yung thermal gradient. And at this particular point is yung magkakaroon tayo ng parang normal na nucleation and growth. Ano? So yung mga dendrites na nag-fall off or mga kumbaga nag-redissolve from this columnar growth, magkakaroon na siya ng parang nucleation sites. Tapos dahil dito, kumbaga masyado na makapal itong layer of solid na to, meaning insulated na talaga yung liquid natin. So yung retained heat is very kumbaga mataas yung retained heat, and therefore slow yung magiging niya, yung heat transfer. And therefore in this particular case, ang mangyayari is yung growth natin is now faster than nucleation. So konti lang yung nucleation sites dahil wala tayong enough energy to overcome the nucleation, stable nuclei na requirement, no, dahil konti na lang yung undercooling natin because of the slow thermal gradient, and therefore mas faster yung growth, no. So mangyayari is we produce large na grains dito. So these are very large grains and it's equiax, no, meaning wala siyang equal sila yung direction in all or equal yung size in all directions. Okay, so I won't go into this grade multiplication. Pwedeng skip ko na lang diretso siguro sa segregation, no? And wala pala akong ano dito. Sige, okay lang to. Wag na natin i-discuss yung segregation. But technically, ang segregation is just when you have a localized compositions, no? And yung localized compositions will lead to parang segregation of the different na micro-constituents. Sometimes segregation can cause chord structures, no? So parang ganyan. Tapos may coring tayo na mangyayari. Chord. Pwede rin yung segregation natin is along the grain boundaries, magpo-produce siya ng mga segregated particles na ganyan. So it depends on the type of segregation. No? So may two levels siya, yung micro segregation which is on a smaller scale. Tapos macro segregation naman pagka parang yung distance na covered nung segregation is larger, no. And usually itong mga segregation na to, this is the bane of any alloy because segregation almost often means that the material is compromised, no. When you have kumbaga lalo na pag drastically different yung properties ng segregated particles versus the host material, no? There are cases wherein segregation is useful, pero most of the time segregation means na magkakaroon tayo ng uh, magkakaroon tayo ng pangit na microstructure that is compromised, lower yung niya, yung magiging mechanical properties, and eventually may lead to failure, no, dahil sa segregation na yun. Okay? So wala na tayong masyadong time, no, pero um I think I have to cover the elements of grain boundaries, no. So if you have another class or meron kayong iba pang gagawin, then you can just leave the session. Nire-record ko naman siya. Tapos but if you have free time, pwede naman you can stay with me until I end the lecture, no. So probably I'll take an additional 30 minutes to discuss the elements of grain boundaries, no. Okay? So again, if you have something else to do, then you can leave the session now. And if you are not doing anything, then just stay with me, no. Tapos if you have any questions, just ask them away, no. But before I proceed with elements of grain boundaries, meron bang question so far about solidification? I know it's sort of medyo theoretical na to, no. Parang mahirap na kumbaga itong part ng topic na to, medyo theoretical siya, wala masyadong calculations, and it involves a lot of parang thinking lang, no, or theoretical na conceptualization. Hopefully na susundan yun pa rin naman. Okay? Questions? Wala naman. So, I'll proceed with yung elements of grain boundaries na, no? So, let me open elements of grain boundaries. Open with saan si Edge? Wait lang. Yeah, okay. Okay. Yeah. Nakikita ba yung ano ko? Self potato. Okay. So this is elements of grain boundaries. And here we'll discuss dislocation models, degrees of freedom, surface tension, and the Hall-Petch relation. No? Okay. So in grain boundaries, or when we say grain boundaries, usually parang obvious to, no, pag when we look at microstructure. So if you have for example, meron tayong ganyan. So it's obvious na kung nasaan yung grain boundary, no? Ito siya. So but if you think about it, what exactly are grain boundaries, no? So meron ba siyang physical representation? Kasi if you think about it, lahat ng mga if you look at a kumbaga nanoscale na, lahat ng mga contained dito sa ano, sa grains na to are just atoms as well, no? Na meron silang crystalline structure. So kumbaga pwede siyang magkaroon ng crystalline structure na ganyan. So yung crystalline structure dito is not much different than this one, no? Tama? O parang kumbaga it still has the same crystalline structure. Kasi if it's the same material, then therefore dapat same lang sila ng parang ano, no, mga lattice parameters. So, does it mean na dito sa boundary na to, this exists as meron bang atoms dito na naka-line na ganyan? Okay? It's something that at the start parang medyo naging ano ko din to, no? Parang confusion din when I first learned about grain boundaries. Is it a physical boundary na merong kumbaga physical na ano, mga atoms na nandyan? Well, physical itong mga grain boundaries actually na to, no, is 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 actually just a representation of the misorientation, no? So when you have long range na crystalline order, um for example, this is a long range crystalline order, no, and it produces a particular na parang orientation ng grain. So for simplicity's sake, I'm just drawing something that looks like this, no? So itong parang grid pattern na to. So just imagine na ito ay crystalline structure to. Now imagine na kasi hindi naman all of the time kasi random lang naman, no? If this starts out as a nuclei, so maliit na nuclei tapos nag-form siya ng crystalline structure such that it forms a large grain, hindi naman necessary na yung katabi niyang grain, same din yung orientation dito. Kung nagkataon na same sila ng orientation, then actually ang mangyayari is, kung same sila ng orientation, you won't be able to see a grain boundary. Okay? So a grain boundary is a when you have misfit, no? So misfit or misorientation. So anytime grains are misoriented relative to each other, then you will notice a grain boundary. So again, as I was alluding to earlier, no, kung meron kang ano, mga grains dito, again, it won't have the same kasi random to, it won't have the same orientation. So pwedeng ganito yung orientation niya. Okay? So kung ganyan yung orientation niya and it meets a grain that has a different orientation, ang mangyayari is because of the misorientation, it will manifest itself as a grain boundary. So that's what grain boundaries are essentially, no? They are misorientations of the crystal lattice or disruptions of those long-range crystalline order. Okay? So ito yung keyword na to, disruption of the long-range crystalline order. Okay? So grain boundaries are quite important though because uh, based on kahit dun sa MetE1 you've learned na sobrang laki ng impact ng grain boundaries natin. In fact, kumbaga one of the strengthening mechanisms that you have learned in grain boundaries in MetE1 is yung grain boundary uh, adjustment, no? Or anong tawag doon? Grain size strengthening, which means that you lower the grain size so that you increase the grain boundaries, and by increasing the grain boundaries, you increase the strength of the material. No? So grain boundaries have a huge impact on the mechanical properties, and one of the few things that are the few scenarios um, that exemplifies this is yung yung tinatawag na transgranular fracture and intergranular fracture, and this is are more advanced na types of fracture, no. So in transgranular fracture, this occurs usually at low temperatures, and as a rule of thumb, grain boundaries are quite strong, no, as compared to the host metal, and that's why yun nga yung common na natin grain size, yung common na strengthening mechanism natin is to produce fine grain structure kasi we know that grain boundaries are stronger than the actual grains. So when grain boundaries are stronger than the actual grains, ang mangyayari yung path of propagation ng isang fracture would be across the grains, no? So transgranular yung nature. So it will be across the grains, parang ganyan, because this host phase here is much weaker than the grain boundaries. Now, when you proceed with higher temperatures, no, and at much slower strain rates, and this condition usually is a condition of creep, no? Hindi ko alam kung na-cover nyo na, but creep will be covered in also 179, no? And actually, no, hindi pala. Totally different pa rin. Pero yun, creep is a condition wherein nasa mataas kang temperature pero yung strain rates mo is low. Tapos ang strain conditions din is lower than the actual na yield point of the material. So it's a very kumbaga what's the term? Parang sneaky. Ano yung ba yung proper term? Basta parang gano'n, no? Sneaky siya na type of fracture because it can go undetected, no? Hindi mo mapapansin na nagkaroon na pala ng creep yung ano, and often it results to catastrophic failure, no? Kasi undetected siya tapos bigla-bigla na lang nag-fail na pala yung material. So this type of conditions, ang grain boundaries, they actually lose their strength, no? And the metal now is much stronger than the grain boundaries, and therefore the path of propagation or the path that the propagation takes is actually along the grain boundaries, and it's along the grain boundaries, ang tawag natin dyan is intergranular fracture. Okay, so in this advanced no, mga conditions, actually mas malaki yung effect ng grain boundaries. So how you manipulate your grain boundaries will tell you kung paano mo ma-strengthen yung isang material. So for example, and this is related to creep na sinasabi ko, no, for creep applications, mas gusto actually natin na mas larger yung grain boundaries natin, no. Mas larger yung grains natin to eliminate or to reduce the number of grain boundary area. Okay? So which is counterintuitive, no, kasi we always learn na no, smaller grains equals stronger material. So there are specific cases wherein larger grains will be more, ang tawag natin dyan is creep resistant, no? So if you know that your material will undergo creep based on its application, then it will be beneficial na i-adjust natin yung grain boundaries such that i-larger natin siya, no? Okay, so I've already mentioned na yung misorientation, no, yung keyword natin when we talk about grain boundaries. Whenever there is a misfit or misorientation, then we have a grain boundary, and we can actually measure this amount of misorientation, no? And this amount of misorientation is what we call as the grain boundary angle, no? Okay, so if you look at this, so this is a yan. So pwede actually natin ma-measure yung amount of misorientation between the two, no? So itong angle na to. Now, if you have a what we call as a low angle grain boundary, this is when you have a misorientation of less than 15 degrees lang. So anything more than 15 degrees, then you have what we call as a high angle grain boundary. Okay. And now this is important because the amount of misfit, so just try to imagine kung mas malaki yung misfit na yan, mas malaki yung kumbaga strain field. Tapos you probably remember something like kunwari may mga lattice ka. So if you have for example a large na interstitial or a large, not interstitial, no, a large substitutional alloy, kunwari a substitutional atom na ganyan. So mangyayari is yung lattice mo is strained, no? Parang ganyan. Tama? I hope you still remember these types of things, no? So parang meron tayong mga straining na nangyayari, no? And even sa interstitial, no? Kunwari may ganyan ka, may interstitial atoms ka, nasi-strain din yung lattice natin. And we found out na yung straining of the lattice, pag nasa-strain yung lattice natin, this is what gives our material strength, no? Because the lattice strain, actually, if you remember, ang theory kasi is based on the dislocation theory is that yung strength ng material natin can be roughly estimated or parang pwede natin siya ma-relate talaga uh, sa amount of dislocation movement that it allows, no? So if it's easier for dislocation to move about freely, then lower yung strength na expected natin sa material. If it has higher if it's very difficult for dislocation movement to occur, then mas malakas yung material natin. And yung hindrances to dislocation could be anything, no? So grain boundary is one of them. Itong mga strain fields is one of them. Ito, kumbaga itong interstitial atoms, that is also another way to hinder grain boundaries. Dislocations themselves also are hindrances to themselves kasi if you look at it, if you produce dislocation forest, nagkakaroon tayo ng hindrances to grain to the movement of the dislocations. And all of this is related to what we call as strain fields. So, strain fields. So if you have a higher strain field, kung mas mataas yung strain field, mas kumbaga meron tayong attraction ng to the dislocations, and the dislocations can only move past a strain field if it possesses enough energy to actually move past that particular strain field. Okay? So it requires energy. So if wala siyang energy to move past the strain field, then it will be stuck or mahihinder mo yung dislocation, and therefore the material is actually stronger. Tama? So, etong mga strain fields na to are not unique to etong mga interstitial or just the interstitial atoms or the substitutional atoms. No? Strain fields can also occur in grain boundaries. So if you have a grain boundary, because etong part, if you look at this, kunwari this is the kumbaga lattice niya, no? Kunwari ito. If you look at it, yung katabi niya is this one right here. Merong misorientation. And this misorientation, because it has a different orientation, nagkakaroon ng strain field dito sa part na to. So along the grain boundary, this grain boundary right here, meron kang strain field. And that strain field is very much, kumbaga, sobrang order stronger siya than the normal strain field na napoproduce dito sa mga interstitial atoms. No? So that's why grain boundaries are actually very kumbaga they hinder, sobrang laki ng paghinder ng dislocation motion niya. Okay? So to illustrate why the angle matters, no? So just try to imagine I don't know, and I'm drawing this very loosely lang, no? Parang i-drawing ko lang siya uh, simplistically. So kung wari may dislocation tayo moving in this direction, if it moves in this direction tapos na-encounter niya tong strain field na to, then parang konti lang yung if it is a low angle grain boundary, no, konti lang yung kailangan niyang parang maneuver or kailangan niyang i-adjust para mag-move into the next na grain, no? So in that sense, kung low grain angle boundary ka, grain boundary angle ka, mas konti or mas maliit yung strain field or strain energy na requirement mo para mag-move past the grain boundary. Now imagine if you were a high angle grain boundary, no? Kunwari, kung pag ganyan siya, tapos yung kasunod is something like ganyan, no? Ganyan yung path. So, for example, if you are this location and you move this, tapos mag-move ka dito, sobrang laki ng parang change of direction na kailangan mong gawin. And that involves a lot of energy, no? Or a lot of strain energy. And therefore, usually nasa stuck tong mga yung mga dislocations na to dito sa or nagpa-pile up siya doon sa grain boundaries natin. That's why high angle grain boundaries usually mean na mas malakas yung strength niya. Okay? As compared to the low angle grain boundaries. So you can look at this ano no, uh, this graph right here. You'll notice that the higher the amount of misorientation, mas mataas yung boundary energy that is contained in the misorientation. Okay? So, this is the stress field produced by the grain boundary. Although the stress field of the grain boundary is so large, ang problema lang is hindi long range yung stress field na yun, no? Or hindi naman siya problema. Pero kumbaga ang ano niya, ang isang consequence niya is that hindi siya long range. So if you look at this is the number of Berger vectors or kumbaga distance away from the grain boundary. You'll notice na sobrang taas ng stress niya if it's very near to the grain boundary. But if you go further, parang almost nagdi-diminish na siya, no? So, the stress field that the grain boundary introduces is only strong when it's near the grain boundary, no? Anything that is farther from the grain boundary, kung baga within the grain na siya, kung within the grain somewhere here, kunwari, yung dislocation mo, nagmo-move siya dito, then mas likely mahihinder yung dislocation mo from movement through other means, no? Hindi makaka-affect masyado yung grains na to. Okay? So, ito yung ano natin, no? This is what we call as the 5 degrees of freedom of a grain boundary. So, when you have a grain boundary, you have actually 5 degrees of freedom. So, you have if you have we have two axes na pwede natin tingnan, no? We have the tilt axis. Ito, this is a tilt axis. So if you have a tilt axis that looks like this, pwede mong i-tilt siya this way. Pwede pa ganyan. Pwede rin siyang mag-tilt the opposite way, no? So, kumbaga, pwede mag-tilt yung boundary. Wait. Sorry. So ito yung tilt axis, no, tapos meron din tayong another one known as the twist axis, no. So ito twist axis naman to, where the boundary twists along this axis right here. Tapos pag tilt naman, the boundary is tilting along the kumbaga nagmo-move siya separately across the along the tilt axis, no. So mahirap siya ma-imagine dito, pero anyway, this just means that this makes more sense, no, pagka nag-discuss na tayo sa movements of grain boundary. So pwede siguro skip lang natin muna itong part na to, itong tilt boundary and twist boundaries. We proceed with surface tension muna, no. Ito surface tension, we mentioned before, no, I mentioned before dun sa MetE176 that that surface tension is actually a very important concept when it comes to physical metallurgy, no? And this is one of those topics that we can really use the concept of surface tension, no? So if you have, let's just say, three crystals, no? Meron tayong three crystals na ganito. Crystal 1, crystal 2, and crystal 3. And they are different crystals, no? Or pwede silang same crystal but in different crystals. Basta the matter is magkaiba sila ng orientation, kumbaga. So they're treated separately. And therefore, pwede tayong mag-produce ng parang surface tension, no? So this sigma A right here, this is the surface tension of the interface between, kumbaga, crystal 1 and crystal 2. This is C is interface between crystal 2 and crystal 3. Tapos itong B naman is interface between crystal 1 and crystal 3. Parang ganun. So it has a so we can imagine this as a triple point, no? Parang ganyan. So we have a triple point that looks like this, and if you studied statics, no, nakalimutan ko kung ano yung law na to. It's a sine law. What was that law? Nakalimutan ko yung pangalan ng tao, no, pero if you have a kumbaga static forces that are in equilibrium with each other, and we assume that is already in equilibrium, no, kasi hindi naman gumagalaw na to gray na to, if it is in static equilibrium, pwede actually natin ma-measure yung angles in relation with each other, no, if we know the sigma values. So if you have by the way, we call this as dihedral angles, no? Dihedral angle. Okay, so this is a dihedral angle, this is a dihedral angle, and this is also a dihedral angle. Okay, so yung relationship niya is that yung sigma A over the opposite na, so if this is your, I don't know, surface tension right here, or the surface energy, yung opposite na dihedral angle, which is this one, yun yung gagawin mong divisor. So sigma A over sine A is equal to sigma B over sine B is equal to sigma C over sine C. Okay? So if you know these angles, then you will be able to compute it. Now let's imagine na meron tayong, I don't know, same crystals. Kunwari, this is of the same material lang. Puro same crystal sila. If it's the same crystal, then therefore it's expected na si sigma will be the same. No? Kasi baga ito, this is, let's just say crystal 1 is, let's just say copper. No? So a phase of copper, kunwari siya. So technically ito, sigma A is just copper-copper interface. This is also a copper-copper interface. And this one as well is a copper-copper interface because they are the same material. So therefore, kung same sila, then they have equal sigma values. Okay? And therefore, kung equal yung sigma values and based on this relationship, dapat it makes sense that their dihedral angles will be the same as well. No? So if it's the same, we have 360 degrees around this triple point right here, 360 yan. So 360 divided by 3 is 120. And therefore, if you have a triple point and it's single, if it's a parang a equilibrium phase, usually they should form a 120 degree angle. No? So, and this is observed in most metals. No? So whenever you see a microstructure that looks like this, well, if you look at triple point, to this is dihedral angle 120, 120 yan. Tapos ito, kahit take a random dihedral angle, no? Ito, 120 din yan. So yun yung natural tendency ng mga materials, no? That are in equilibrium. If you leave it for a long enough time, eventually they will form parang mga ganitong shape, no? Parang medyo hexagonal shape siya. Tapos they will form yung boundaries nila will always form triple points that have a dihedral angle of 120 degrees Celsius. So this is one of the ways you can determine if kung gaano ka tagal na yung metal inanneal, no. Usually pag inanneal kasi natin siya, ina-allow natin yung diffusion of the solid atoms, no? Tapos or the metal atoms, and when diffusion occurs, then they will reach a configuration that is the equilibrium configuration that is thermally or that is energetically favorable, or at the lowest energy possible, and this is the lowest energy possible na configuration, no? So well annealed metals, single phase metals will always have dihedral angles triple points of 120 degrees Celsius. Okay? Now, let's imagine na kunwari hindi siya single phase lang, no? Mayroon tayong different phase. Kunwari meron tayong phase 1, two phases, no? Kunwari ito yung tawagin natin the second phase, no? Usually pag sinabing second phase, we almost always mean precipitate, no? So if it's the first phase usually means the host phase. Tapos pag sinabi nating second phase, this means the second phase means that it is the precipitate. Precipitate. Okay. So if we have the second phase here, phase 2 is the precipitate, phase 1 is the host phase. So if you have something that looks like this, then therefore you can notice na etong si sigma, etong tatlong ano natin, na surface tension or surface energies will not be the same anymore, no? As opposed to before, kasi same sila if you use the sine law, no? Itong sine law na to, we have equal dapat ang sigma, which means equal din ang angles, ang dihedral angles between them. In this particular case, hindi na siya equal, no? And I'll leave the derivation to you guys. Pero basically, we will get something that looks like this. Sigma 1, 1 Kasi this is the interface of phase 1 and phase 1. Tapos ito naman, sigma 1, 2 because interface to ng 2, the second phase and the first phase. Tapos ito rin, it's the same value, no? Kasi same interface siya. It's an interface between the second phase and the first phase. Okay? So, etong sigma 1, 2 right here is the same as the sigma 1, 2 right here. Okay? So, ito lang na iba. Ito si sigma 1, 1. So, if you do the math, you will end up with something that looks like this. That sigma 1, 1 is equal to 2 times sigma 1, 2 cos theta over 2, where theta is the dihedral angle between the two um, across the second phase. No? Okay? So, um, this dihedral angle right here is if we rearrange this, no, parang if we do a ratio, no, ito if sigma we can rearrange it to look like this. Sigma 1 2 over sigma 1 1 is equal to the 1 over 2 cos theta over 2. Again, sigma 1 1 is the host phase. Ito yung tinatawag nating interfacial na dihedral angle, no? So interfacial siya because it is an interface between two different phases, no? So itong si sigma 11, although it's still an interface, pero kumbaga in this context, they are the same phase, but so sigma 11 lang siya. Okay? So parang ganyan. If we try to graph this, you will notice that the graph will look something like this, no? Parang ganyan. This is the ratio between sigma 1, 2 and sigma 1, 1. So if you have a lower ratio, no, meaning that sigma 1, 2 is, kung sigma 1, 2 is lower than sigma 1, 1, so this line right here. So anything below that, you actually produce a dihedral angle that is lower than 120 degrees, which is the equilibrium. No? Ito kasi yung equilibrium natin. So anything lower, we will produce a smaller dihedral angle. No? So parang mga maliit na interfacial dihedral angle yung mapuproduce natin. Anything larger, so if sigma 1, 2 is larger than sigma 1, 1, then this is the case. No? Ito, sigma 1, 2 is larger than sigma 1, 1. Sorry, this would be less than. So if it's lower, then the dihedral angle is less than 120 degrees. If it's higher naman, if it's higher than sigma 1, 2, then you will expect na greater than 120 degrees yung mapuproduce mo na interfacial dihedral angle. Okay? So this is important because actually makakapag-produce ka ng mga unique cases dito, no? So try to imagine na meron tayong dihedral angle that is lower than 120 degrees. So this is a case where sigma 1, 2 is lower than sigma 1, 1. Okay? So if you look at this, this is the second phase, no? So this is our second phase right here, or our precipitate. Tapos, if it's lower than sigma 1, 2, if sigma 1, 2 is lower than sigma 1, 1, ang mapuproduce natin is a dihedral angle equal to 120 degrees. No? So parang ang mangyayari is, this is a very low dihedral angle. Pero there can also be, kumbaga, ang tendency niya is that it will produce parang a network, no? Parang ito. So ito. So sometimes hindi siya masyadong detrimental pagka ganyan lang siya. If it's not so low, no, kung itong dihedral angle dito is not so low, then you could produce something that looks like this. So parang meron kang pseudo triple point dito, no, wherein ito mga first phase to nandito. So this is first phase, ito first, ito rin first. So host phase yan lahat. Tapos in between the three, meron kang parang second phase lang na ganyan. So it wouldn't really matter that much. Hindi siya masyado makaka-affect. Pero what does affect it is if sobrang nipis nitong dihedral angle na to. No? So ang mangyayari is if sobrang liit niya, something like this, no, sobrang maliit, mangyayari is ang tendency niya is magpuproduce siya ng network, no, along the grain boundaries, parang mga ganyan. Sobrang haba na network such that it produces a thin film, no? Parang mangyayari is itong thin film na to is surrounding every grain. So parang grain boundary na ganyan. Tapos may thin film ka of the second phase. Ito yung grain boundary. So this is very detrimental, no? Lalo na pag this is a weak phase. Kasi despite being a strong phase, itong kunwari, strong yung first phase mo, pero yung second phase mo is very brittle, mangyayari is sobrang brittle ng material mo. Kasi the fracture will occur at the grain boundaries, no? So para mangyayari is transgranular yung intergranular yung magiging type of fracture na ma-experience ng material na to. And this occurs for ang um, pinaka common example nitong or staple example nitong itong producing a continuous network, which is very detrimental whenever it produces a continuous network, a thin film of continuous network that surrounds the grains themselves. A staple example is yung sulfur in steels, because sulfur in steels, ang nangyayari kasi is they produce precipitates that have a very low dihedral angle, no? And this low dihedral angle na sulfides, it could be any sulfide. Pwede siyang FeS, pwede ring manganese, MnS, o pwede ring ano pa bang ibang sulfides. But it's usually a metal and or kumbaga metal sulfide, no? When you have a metal sulfide, usually they are brittle, no, yung mga metal sulfides, and they have a tendency to line the surface, no? So even if they exist in very small amounts, ang napoproduce nila is kumbaga a large network, no, that covers that has a thin film along the grains, no? So nangyayari is nagiging sobrang brittle ng steel natin, and they have a term for this. Ano ba term nila ito? Hot hot shortness. So this is one of the cases we're in detrimental C. Let me confirm. No? Hot shortness. Parati ako nalilito ito kung hot shortness or short hotness. Hot shortness in steels. Okay. So parang na nagsusulit pagka dito nagkakaroon tayo ng cracking along the grain boundaries dahil dun sa production ng manganese. Not specifically manganese na sulfides, but production of sulfides. So it produces catastrophic failure, and it's very detrimental to steels. No? So and there are other examples of this, pero ganito yung behavior niya. So next naman is if we have the sigma 1,2 is greater than sigma 1,1, meaning nandito siya sa area na to, no? So it has a dihedral angle greater than 120 degrees. And if it's greater than 120 degrees, usually, hindi ganun ka-detrimental yung effect niya. No? Kasi ang nangyayari is, instead of being a continuous network, ang nangyayari lang is, it forms globules. No? Ito mga globules na to. So globules siya kasi, again, mataas kasi yung niya, no? Angle niya. So usually, it doesn't even have to be sigma 1,2 greater than sigma 1,1, no? As long as the ratio produces an angle that is around greater than 60 degrees. So if it's greater than 60 degrees, so kahit sigma 1,2 is less than sigma 1,1 pa yan, basta the dihedral angle you produce is greater than 60 degrees, ang tendency niya is to produce globules, no, instead of a continuous network. And that globules have no, or may effect siya, may konting effect, pero hindi ganon kalaki yung effect niya sa performance ng grain boundaries. So globules are safe. So, okay. So this is the last part of the lesson. This is the Hall-Petch relationship. No? So the Hall-Petch relationship is a relationship that describes the strength, usually in hardness. No? Pwede rin in terms of yield strength in sigma. So the hardness is equal to a constant H naught plus a constant K multiplied by D raised to the power of negative 1/2, or this is pwede rin KH over square root of D. So this is an empirical equation, no? Brought about by experiments of Hall-Petch. Parang napansin nila na as your grain boundary decreases, or kumbaga as your grain boundary if the surface area of the grain boundaries, that is saying na kung mas mataas yung surface area ng grain boundaries, that is saying na mas maliit yung grain size mo. So D here is the grain size, no, the average grain size expressed in microns. So if you have a smaller grain size, then you have a larger na mechanical property. In this case, hardness, ano, and it actually follows a straight line, no, and parang this is a y equals mx plus b na type of equation, no. So it follows a linear na equation wherein yung x natin is the square root of d. So where square root of d is the square root of the grain size, no. So as you increase the grain size, you decrease your strength kasi parang inversely proportional siya, no. Tapos pagka dinecrease mo naman yung grain size, so kung mas maliit yung grain size mo dito, mas maliit yung denominator, therefore mas mataas yung overall value na to. So you increase the hardness, and the same goes for for strength as well, no. So um, the Halpert relation also affects. So if you have sigma, yung strength natin is equal to sigma naught. This is the constant, the intercept. Tapos if you add this is another constant, no. This is also a material constant multiplied by d raised to the power of negative 1/2, which is just k over square root of d, no. Again, uh, the same behavior applies, no. That if you increase the grain size, nagde-decrease yung strength. Tapos pag in-increase mo naman yung pag din-increase mo naman yung grain size, nang-i-increase naman yung strength. Okay? So, I think you already know the Salpetch relation, no, from MetE1. All right. So that's everything you need to know about grain boundaries, no? And sakto nag-extend ako 30 minutes. Actually, mga 40 minutes pala in-extend ko. Anyway, so thank you. Shoutout kay Hans Eric kasi nagstay siya hanggang sa dulo, no? So, yun lang. I hope you uh, learned a lot from this synchronous session. And if meron pa kayong further questions, no, pwede sigurong email nyo na lang ako or type nyo dun sa Google Chat natin. Tapos i-upload ko na lang yung recording na to for those who were not able to join us today, and for those na hindi rin, for those na early nag-exit, no, or hindi man early, saktong time na nag-exit, no, kasi nag-extend nga pala ako. So thank you again for joining today, and Hans, thank you for staying up until 3 o'clock, no.
Thank you po.
Okay, and I'll see you next week siguro, or depende na lang kung ano yung schedule natin. Pero most of the topics naman meron ng recordings, no? So baka hindi na natin kailangan mag-meet sa other topics apart from siguro ano na lang, consultation na lang. Okay?
Oh.
Okay, so thank you, and I'll just close the session right now.
Thank you.